This is actually a teaser for my lecture at École Normale that I started this year. And the aim of this lecture is to kind of nucleate a double curriculum for students between economics and physics. I'm not sure it's going to work because there's a lot of inertia and resistance, but this is promoted by the physics department and with the hope of getting economic students and then maybe later on really create something that takes into account both cultures. Anyway, so that's my little teaser, and so I'm going to run that through you. So it's customary to quote this paper, More is Different, by Philippe that everybody knows. I think it's a remarkable piece that's cited by even philosophers. Phil Anderson is clearly one of my heroes. And I've rewritten a little bit this piece in order to make it more adapted to my topic today. So he says the behavior of large assemblies of interacting particles, which are replaced by individuals, cannot be understood as a simple explanation of the properties of isolated individuals. Instead, entirely new, unanticipated behaviors may appear, and their understanding requires new ideas and methods. Statistical physics has been developed to describe these selective phenomena, that's more me, by the way, at this point, pertaining to crowds and not to any of its single constituents. Small changes at the individual level can trigger dramatic effects at the collective level, for the better or for the worse. So this idea I illustrate with concepts that are well known in physics, but are not so well known in economics, where this idea that interactions can completely change the game is not so well accepted or even known. Okay, so my behavior or dark corners, and I'll try to explain why this title, dark corners. So as you all know, fundamental concept in statistical physics, but again not that well known by economists, is that of phase diagrams in parameter space. And so we are very well used to the phase diagrams of substances, the temperature pressure plane, where different phases appear. And what we know is that within each of these phases, say the solid, properties are always more or less the same. The solid is a solid, the liquid is a liquid. It doesn't really matter what molecules constitute these phases, they always behave more or less the same way. Maybe the viscosity is slightly different, parameters are different, but the basic large-scale properties are the same. And also, linear theory is valid. Small changes lead to small effects. So the lesson from this that we tend to forget, and that's my illustration of this iceberg here, and that we are so used to that we forget that it's spectacular in a way, is that the macroscopic aggregate properties are robust against changes of microscopic details. Only a few emergent quantities are relevant to describe the substance, but on the contrary, when we're close to a phase boundary, then small changes of parameters like temperature can completely change the microscopic appearance of the substance. So again, I think we were so used to it that we don't think about it, but it's hard to believe that this very same molecules are actually responsible for these two states of matter that don't look alike at all. So, dark corners. So I want to contrast this with what Olivier Blanchard, who was the chief economist at the IMF, wrote after quite a long time actually after the crisis. He wrote a very insightful piece that I recommend to you all, called Where Danger Lurks. And he writes the following: we in the field of economics did think of the economy as roughly linear, constantly subject to different shocks, constantly fluctuating, but naturally returning to its steady state over time. The main lesson of the 2008 crisis is that we were much closer to dark corners, i.e. situations where the economy could badly malfunction than we thought. So the idea of this economic model is really the picture of a marble in a ball. You know, shocks, but nothing really happens, it just wobbles around a stable equilibrium. Now that we're more aware of nonlinearities and the dangers they pose, we should explore them further theoretically and empirically, trying to create a model that describes crisis maybe beyond the profession's conceptual and technical reach at this stage. What's strange is that after this piece in 2014, Olivier seems to flip-flop between defending the old schools and trying to promote new ideas. So it's not very clear, and I met with him 2 years after he wrote the piece, and I was pretty depressed at the end of my conversation because he seemed to say, well, anyway, we're back to usual business and nothing will happen. Anyway, so coming back to statistical physics, we know that establish the phase diagram of a model from, sorry, I failed to say something important, but I guess you all understood. The idea here will be to try to explain that these articles that Bouchaud speaks about may be thought, at least as a kind of conceptual framework, as these phase boundaries that we know about. So of course it's a naive point of view, but I'll try to explain why already this naive point of view may be useful. Okay, so what we know is that from single constituents to guess what's going to happen on large scale is extremely difficult, actually. And it's one of the main achievements of statistical mechanics. So we've had several aspects of statistical mechanics yesterday, kinetic theory and so on. I think the idea of phase diagrams and the idea of emergence is, to me, one of the greatest aspects of statistical mechanics. So the behavior of some phases, like the gas phase, are easy to guess, but some other phases are genuinely surprising. Think about superconductivity, for example. Nobody had imagined before it was discovered that through interactions, something like a collective phase that would flow without resistance could be possible. And so I've emphasized this, but again, I'll emphasize it again. The micro and macro behavior need not and do not coincide in general. And this is relevant because often in economics, models replace full community of agents by what they call a single representative agent, which is a single man supposed to represent the whole community. Okay, so let me give you a few examples of collective states, some from physics. And again, I'm going to cite Phil Anderson because he said something very profound, I guess, about rigidity, about solids. He said we are so accustomed to the rigidity property that we don't accept its almost miraculous nature, that it is an emergent property not contained in the simple laws of physics, although it's a consequence of them. And if you think about it, it's true that it's remarkable that a crystal doesn't flow when all the single molecules constituting the crystal are still able to diffuse around freely, and not freely, I mean it takes some energy, but each single atom can, if you follow it in time, it can go as far as you want, if you wait long enough. But as a whole, the system is rigid. So we know many examples of that, of this emergent property, magnetism, superfluidity. Theory has started with say Van der Waals or Curie-Weiss in 1905, 1910, but it's continuing now, as we all know. It's still a very active subject in statistical physics, and it has spilled over to some extent to social sciences and economics. So although I told you earlier that these concepts are not so well known or well used in economics, there are counterexamples like Thomas Schelling or Granovetter, who have emphasized the importance of interactions, and I'll go back to the Schelling model later on. So again, very same individuals, very different societies, and this is not specific to physics. So examples, this has been mentioned yesterday, this is a very spectacular effect called starling aglomerations. Why do these birds do this, and how do they do this, these amazing patterns in space? As you all probably know, this has been now well studied by the group of Andrea Cavagna and Irene Giardina in Rome. And what's striking, and you maybe won't believe it, but when I show these pictures to people who are not used to physics thinking, for example, they all believe there's a leader. They all believe that there's a belt somewhere that gives the direction to all others. But actually, it's obviously, I shouldn't say obviously, it's not true. These things self-organize in such a state. And this state has some kind of rigidity because the whole pattern here can change direction in less than 0.5 seconds. So the fact that they're in a kind of cohesive state means that 10,000 birds can, in case of danger, for example, suddenly change direction extremely quickly. So there are other examples. Fish schools, one that I like very much is the stories of fireflies that maybe some of you know already, but again, this is not such a well-known story in the end, although it's now several years old. So I'm going to read a paragraph from the introduction of Stephen Strogat's book, Sing the Emerging Science of Spontaneous Order, where he describes the story of fireflies. He says, for 300 years, Western travelers to Southeast Asia had been returning with tales of enormous congregations of fireflies blinking on and off in unison in displays that stretched miles along the riverbanks. How could thousands of fireflies orchestrate their flashing so precisely and on such vast scales? For decades, no one could come up with a theory. A few believed there must be a maestro, so again, leader, a firefly that would cue all the rest. Only by the late 60s did the pieces of the puzzle begin to fall into place. And as we know now, I mean, this is the story of synchronization of neurons and the Kuramoto type models to explain these behavior. We humans do strange things as well. I like the Mexican wave story. I don't know if you've seen how a Mexican wave appears in a stadium. It's really interesting. It's really nucleation. And this is a good example, again, in statistical mechanics classes, because you can argue that it requires a certain number of people, some nucleus to actually start the thing. And if you look closely, people try to start it, 3 or 4 of them, and nothing happens. And then suddenly, by accident more or less, 20 people do the same thing together, and then it starts. And what's interesting also from the point of view of phase transition is that actually a Mexican wave could propagate clockwise or counterclockwise. So there's also the idea of symmetry breaking that appears. So spontaneously, the wave decides to propagate in one direction rather than the other. There's another very anecdotal example where I was the witness of that. So this is a picture of Pont des Arts in Paris, joining the French Academy with the Musée du Louvre. And so now it's gone. All this is gone. They've changed the organization of the bridge. But anyway, so probably you've seen that before, but these are love locks. So people put these love locks on the bridge. And in a matter of weeks, as I was crossing this bridge every day to work, it went from a few love locks to the whole bridge being covered with that. So there's a clear interaction effect here. Capping, I'll talk a little about this later. Fads and fashion. So of course these are all very innocuous examples. There are more serious examples where interactions, collective effects play a role, like vaccination campaigns, voting patterns, money, cat money, of course. This is important that we all coordinate around something that we trust. And of course there are more scary effects like mass panic, in stadium, bank runs, market crashes, mass effects, mass enrollment, like this, And so I like the quote from Life of Brian Monty Python. Some of you know this quote, but look, you've got it all wrong. You don't need to follow me. You don't need to follow anybody. You've got to think by yourselves. You're all individuals. The crowd. Yes, we're all individuals. Brian, you're all different. Yes, we're all different. I'm not. Okay, so collective states emerge as a result of repeated interaction between individuals without the need of any exogenous signaling. And that's really the beauty of these effects. The influence feeds back and creates a self-sustained, self-validated state that is different from the state where there are no interactions. And of course, very precise statements can be made in physical models, and I'll give you a few examples in the social area later. So if you think of birds, birds, if you're a bird, I take cue of my direction from you, and you take cue from him, but he takes cue from me, and this results in a collective state where the flight direction emerges from actually weak individual biases that lead to a collective state that can flow in one direction, but no leader. And if you change direction by decision, you have the same kind of effects in human communities. In particular, trust networks, and as I've said, this is a prerequisite for many economic phenomena. Business requires trust, or actually works much better when trust is shared. And if you have things like I trust you because he trusts you because I trust you, then you can have self-fulfilling trust phenomena that occur, that are good, but they can also disappear, and I'll comment on that later. So it's really interesting to see that repeated local checks between individuals may result in rigidity, that is, synchronized group behavior. Information can travel long distances even though there are only nearest neighbor interactions. So again, this is of course well known to most of you here, but for students who discover this, I think this is really striking. And the interaction travels, or the information travels with little degradation. And if you think about Chinese whispers, so I don't know what's the Italian name for that. In French it's téléphone arabe, the game where you whisper to your neighbor information and then it gets degraded along the chain. So is there a name for this? Okay. So no reference to any special people. So we know that if one has a one-dimensional chain, information gets degraded. But if you have many loops that self-correct information, then it can travel very long distances. And this was noted by the Rome group on starlinks, where they say that each animal in this collective state has an effective perception range much larger than the direct inter-individual range, and this enhanced their global response to perturbations or threats. So there's a shared knowledge about direction in the case of birds, of decisions in the case of humans. There's no need of a leader, no maestro, no external cue, or if there is an external cue, as we know, these states can have a very large susceptibility or be hypersensitive to it, like the bird reacting to external threats. So, as I've kind of alluded to already in the case of trust, the problem with collective states is that they can suddenly disappear or appear upon small changes of parameters or external conditions. And this is a very natural scenario for crashes, landslides, discontinuities of all kinds. The idea of a discontinuity, the idea that you change a parameter and the response to that parameter can be absolutely discontinuous, is not included in traditional economic models. As I've said, you think again of the marble and the ball, nothing much can happen there. So, for example, for me, I was really struck by what happened in 2008. I was not the only one, of course, but if you remember what Barack Obama said during his inauguration talk in January 2009, he said, "Our workers are no less productive than when this crisis began. Our minds are no less inventive, our goods and services no less needed than they were last week." But still, in a matter of a week, everything had changed. As if, it's very striking, in particular for economists, because nothing material happened. There was no destruction of anything. It was just suddenly that people didn't trust in the economy anymore. You know, I know stories of people running to the bank in New York and getting out of the bank with a plastic bag full of banknotes. This happened. And if you were in New York in October 2008, you may remember that shops selling electric devices or, you know, mundane things were empty. I mean, suddenly people stopped doing anything at all in the economy. So this is reflected, for example, by this graph here. I won't go into the detail, but the red curve is a fear gauge in the way that it measures how the interbank lending market functions. And when this peaks, it means that banks stop lending to each other. So that the banking system just froze suddenly in October 2009, as if nobody trusted any bank anymore, and this was a kind of self-fulfilling process. So what's interesting is that you can make generic models for trust networks. And so this is a model that we've looked at, but several other people have devised different versions of this model, where you have a network where links can be created between individuals, think of banks or just agents. And the probability to create a link depends on the number of already existing links in a kind of self-fulfilling process, like I trust you because you trust you because I trust you. And so in these models, you have a generic first-order phase transition between a sparse network, a low-trust network, and a high-trust network. So a badly connected economy, if you want, and a highly connected economy. And so if you look at what happens as a function of a kind of external field, which would be the objective state of the economy, if you want, so that would be, I don't know, call this the intrinsic trustworthiness of the economy, or the news that accumulates. Then if you start from a high trust phase, and the news about the economy starts getting worse and worse, which happened in 2008, but in a kind of progressive manner, then in these models what you see is that you stay on the high branch for a long time in this whole phase coexistent region, before suddenly, as we all very well know, this branch just disappears. So there's no real precursor effect here. There's nothing happening special at this point. It's just that the structure of the underlying network changes, and it's not possible to sustain a high trust network anymore, although the low trust network started existing far before this. So here in this kind of models, the crisis is not induced by a major exogenous shock. Nothing happened here. And that's the way economists tend to think about this, that they think that a major exogenous shock replaces a favorable equilibrium by an unfavorable one. You see here it's very different. It's the fact that there was already a bad state that pre-existed, that was lurking around, as Olivier Blanchard hinted at in his piece. And so it's a different scenario, but I think a very pervasive one. Oh yes, I found that quote by an observer of the stock market in the 19th century, who wrote a lot about, he wrote a full book called Lombard Street, and he said the peculiar essence of our financial system back in the 19th century already is an unprecedented trust between man and man. When that trust is weakened by hidden causes, a small accident may greatly hurt it. Nothing has changed. So, as I've told you several times, collective effects can lead to genuinely surprising and non-intuitive behavior. Macro and micro behavior need not coincide, there's no representative agent. And now I would like to give a few examples, very simple examples of the kind of counterintuitive effects that can occur through interactions. So, again, this is a well-known example to physicists, but not as clear to people who have not been fed with the Ising model since their 20s. So the Ising model can be transposed to socioeconomic situation by assuming that each individual has some binary option for the left or the right, buy or sell, pay taxes or evade taxes, you can invest or applaud or not applaud, and I'll give you real data now in this case. And each individual is influenced by three different types of effects. One is an idiosyncratic factor. So for example, so let me speak about how you applaud at the end of a concert. So you may have liked the show very much, or you may be a friend to one of the performer or whatever. So there's an idiosyncratic component to your willing to be clapping for a long time. Then a second effect that's very important, as we've seen in different examples, is social pressure. So in the case of applauses, it is clear, at least in France, that people are extremely sensitive to the noise made by others. And they don't want to be caught clapping alone like fools. So they will stop clapping just because others stop clapping. And then, oh sorry, there shouldn't be random noise here, I'm sorry. It shouldn't be random noise, it's not influence, which is the idiosyncratic factor, but it should be external, I don't know why this was left from a previous slide, I guess, but anyway, it's point 3 is not random noise, it's actually common information. So in the case of clapping, it is just time that passes, and the more time passes, which is the same for everybody, the less people are willing to continue clapping. So how will the clapping end? But you can rephrase that in many different ways. So another example that we've studied with data is the way cell phones invaded markets. You know, cell phones, clearly now we all have cell phones, but in the 90s, some people were more willing to buy these new gadgets right away. There's a social pressure component, of course, or just the fact that the more people have cell phones, the more useful it becomes to have a cell phone. So it's not necessarily the stupid social pressure, but it may be associated to what economists call externalities, so a real improvement of the performance of the object when other people have it. And then the external news would be, in the case of cell phones, the price of the cell phone or the technology. In the beginning, cell phones were pretty lousy, and as they improved in quality and their price got down, it was more and more, it led more and more people to buy them. And so, as you know, there's a phase transition in these systems between individual and collective behavior, where two self-validated states appear, where everybody buys or everybody sells. And in the case of physics, these two minima corresponding to these two states can have the same depth, i.e. have the same social utility, but they can also have different depth, depending on what we would call the external magnetic field, or this external news component that I talked about. And so what's interesting, and again not that well known to other communities, is that we know that in physics you can be stuck in the wrong phase. That is, you can be stuck for infinite amount of times, or practically infinite amount of times, in a state that is not realizing the minimum of the free energy or the maximum of the collective utility. And it's interesting to see that there's a barrier to cross to go from the wrong state to the right state. And this energy barrier can be so high that, as I said, the whole society can be stuck in the wrong minimum. So if you think, for example, of countries where tax evasion is a national sport, it is mostly due also to social pressure. You know, people think that if they start paying taxes, they are really stupid compared to their neighbors. And in order to try to make the whole society hop from one state to the other, it may not be easy at all. You have to find ways to nucleate and to cross this barrier that can be very large. So let me give you another consequence of this type of model, is that it leads to what economists call aggregate demand, that can be very strongly distorted when you compare what would happen if individuals didn't interact with the case where individuals strongly interact. So if the individuals don't interact at all, say, then as a function, think about cell phone in that direction, and think about time and pauses in the other direction. But let me speak about cell phone first. So say this is the quality of the cell phones, or the inverse price of the cell phones. Then as the quality of the cell phones increases, more and more people are willing to buy. And the blue curve corresponds to the dispersion of idiosyncratic preferences. So this is well known in the context of marketing. There are early adopters, and then there's a more abrupt rise. And then these are the late adopters, which, my grandmother, for her, she never had a cell phone, so she was not interested at all. I guess that she would have been in the tail of this blue curve. So that's an undistorted demand curve, which just reflects the idiosyncratic discussion of individuals. But now if you introduce social interaction, which makes individuals do what the others do, then you can completely transform this blue line, and actually there's a phase transition where this blue line becomes discontinuous as you increase the interaction strength. And so beyond some critical interaction strength, the curve becomes discontinuous. There's a first phase where nobody buys because nobody buys, and then suddenly, a little bit like in my trust scenario earlier, the whole population, actually a finite fraction of an infinite population, jumps to the buy state. So now think of this in terms of applauses. Now time is running in that direction. So if people didn't interact, these guys didn't like the show, so they stopped applauding quite soon, and then most people stop applauding, and then at the end they have a few fans that want to continue applauding forever. And then vice versa, if they strongly interact, they're very afraid of being caught clapping alone, then as soon as you don't see here hidden in the graph, but as soon as the level of applauses starts going down a little bit, the whole thing may collapse. So this is something actually that we've been able to look on experimental data. So we try to collect applauses at the end of concerts. What's not obvious to do is to be sure that the sound engineer didn't fiddle with the sound of the end of applauses. Nobody's interested in the end of applauses, right? So we made sure that these were untreated recordings. And so what you see is that depending on the kind of audience, you have audiences where, so this is the sound made, the total amount of applauses, if you want, and this is time. And so in some cases you find a very smooth decay of the applauses, and then in some cases you find an extremely abrupt drop. And you can actually treat these data and compare the data with what in physics is called the random theorizing model, and that captures the elements that I talked about, idiosyncratic biases, interactions, and so on. And actually try to see whether the shape of these curves, stylized shape of these curves, conform to what the random theorizing model predicts. Okay, another very spectacular model of this kind is called the shedding segregation model. That was back in the 70s, and it's been revisited by physicists recently, and they were able to rephrase it in a way that makes analytical calculation doable. And actually what you will recover is the liquid gas face separation. So in this model, there's a city that's divided in neighborhoods, okay? And there's actually exactly, so if you think of what's plotted here, these are buildings, say, and the population is exactly such that each neighbor could be half filled with people. And actually each individual on his own favors half-crowded neighborhoods. So he doesn't want to live in empty neighborhoods because it's not fun, there are no shops, whatever, and they don't want to live in overcrowded neighborhoods either. So there's a maximum of what economists call the utility function of each individual, which makes each individual favor half-crowded neighborhood. And if he's not in a half-crowded neighborhood, the rule of the game is that he decides to move if he can find a better place for himself. Note that in this rule, he just cares about himself. He doesn't take into account the fact that when he moves, he may change the utility of other people in the neighborhood he moves, nor of the utility of people in the neighborhood he joins. Just thinks about himself. So this is a kind of neutral presentation of the Schelling model. Actually, Schelling was interested in racial segregation in US cities, and so Schelling thought of that as, for example, white and black individuals. And his point was that even if each individual is tolerant in the sense that he agrees, he's happy actually, he's even more happy to live in well-mixed neighborhood, something drastic may happen. And what the drastic thing that can happen is that depending on the parameters of the model, but for a very broad swath of parameters, you find that the outcome of this single selfish rule is to lead to a completely suboptimal, actually the worst case scenario, where the collective state is made of totally empty neighborhoods and totally full neighborhoods. So it's interesting because this is a priori reachable, but the rules of the game make this state highly improbable and lead to phase segregation that we call it physics. So if you look at the way they phrase the model, so this is by Robin, Janssen, Bertin at the INS Lyon, it's really a liquid gas transition. So it's a very nice example where the invisible hand, the idea that if you let people do according to their own good, the whole society will be better off. This is a very interesting example where this invisible hand badly fails. And what they notice as well in the paper is that you can help the system by introducing a kind of tax. And the tax is such that you make people aware of how their action is going to affect others. So as I told you in the rule used by Schelling and basic rule studied by Robin, Janssen, and Bertin, is such that each person doesn't take into account his interaction with others in a way. He just takes into account his change of utility function, but not the change of the global utility of the system. If you help the system by adding a tax which makes people aware that when they're changing neighborhood, they're reducing or improving the global utility, then you can have this kind of behavior. So this is zero tax, the global utility is zero, it's in this state where there's the worst case scenario. And as you increase taxes, you increase the global utility until a critical tax where you reach this state. You help the system finding the well-mixed state. So the mathematics is really beautiful, it's very simple. And I think it's an extremely nice example to teach, and I've done that this year. Maybe a last example is the so-called Defluent-Weisbush model for opinion. So in this model, each individual has a certain opinion, which is modeled by a real variable between minus infinity and plus infinity, which you can think, for example, as a propensity to do something. And I'll give you an example where the propensity is to go and vote or to abstain. But it could be a measure of left-right polarization or whatever. And so in the Diffie-Hellman-Bouchaud model, what they envisage is that individuals meet each other. So if you want to think in terms of kinetic theory, there are collisions in this model. And upon encounters, if the opinion difference, if the difference of this variable between minus infinity and plus infinity is sufficiently small, the opinion difference tend to narrow, so people are able to speak to each other and reach a kind of common ground, if you want. But if the probability for this to happen decays with initial distance, so far away opinions, they meet, but even if they talk about their opinions, they're absolutely unable to reach any agreement and they stay where they are. And between two encounters, each individual lives in his own life, and there's an independent evolution of his propensity due to idiosyncratic influences. You read the press, something happens to you, whatever, and so there's a random walk type evolution of this between two encounters. So what will happen? Well, what happens in this model, which is quite nice, is that there's a phase transition between a socially cohesive phase and a fragmented society. And so if you look at the system as time progresses, you can be in a state where there are subcultures, these blue peaks, and then as time goes on, the opinions can coalesce around a common ground, or not, or be dispersed forever. So again, what's nice, and coming back to yesterday's talk about kinetic theory is a good example. I think this is a very nice example because the Boltzmann equation is much simpler than the Boltzmann equation in gases, because it's a single, one-dimensional model. And furthermore, you don't have to make ad hoc molecular chaos assumption. You make the assumption from the start that people enter random collisions. And you get this space transition after pretty simple calculations. So what's interesting is that you can actually have that without space, which was the Diffie-Hellman-Bouchaud model, or you can embed this model into a spatial structure and say that on top of distance in opinion space, there are also distances in real space. That is, people only meet if they live close to one another. And what's interesting about this is that if you solve the model, the same model, using the kind of Chern-Langenskog expansion in space, what you find is that the correlation function, I mean, it becomes a kind of Edwards-Wilkinson model in two dimension, and if you have three Gaussian fields in two dimension, it's well known that the correlation function decays logarithmically. And what's interesting is that if you look at, for example, a turnout pattern, so the way people decide to go vote or to abstain in different countries, this is what you see. So red regions are regions where people vote a lot, and blue regions are regions where people abstain a lot. And it's clearly, this is not a random pattern. There are spatial correlations. And if you measure the spatial correlations in different countries, so this is France, for example, you find, so this is log of distance between points, and this is the correlation function, you find this nice logarithmic dependence. And actually it's been redone by another group, the group of Maxwell San Miguel in Spain, in the US, where you again see for different elections something that's pretty straight in semi-dot plot. What's interesting is that it holds within the country, but you see here, for example, the boundary between Alsace and Germany. There's a sun jump in the turnout, which means that, and quite obviously, there's a barrier, which is a language barrier.
Is this a European election?
Yes, this is a European election. But you can do that. We've done that on several elections: French elections, European elections. You find the same thing. This is European election, and it's nice because you see these discontinuities that within the model are easily are easy to interpret. So, okay, so I'm done with my 3 simple examples. So as a conclusion, I try to insist on the fact that collective effects are often counterintuitive and defeat our imagination. Think about superfluidity, superconductivity in the physics language, or think about the segregation of people who all want to do the right thing, but collectively fail to do so. So the basic message is that understanding individuals in isolation may totally miss the collective. Collective states may respond disproportionately to small local shocks. And for me, people speak about complex system. This for me is a nice definition of a complex system. The complex system is a system that can respond normally to a small shock, but also, in some cases, abnormally to others. Because when you do a small perturbation, you don't know what you're going to get. And I also have, speaking to a lot of people, I have the feeling that policy making is controversial because we all tend to think about our local scale, our individual reactions, and we have it's very difficult to take a view from the mountain and see the collective. So in order to nail the point to people, I think we need models. We need models to show that in some cases things that are good at an individual level are very bad at a collective level, and vice versa. So collective effects are counterintuitive. So we need models, and we need what Mark Buchanan, just after the crisis, he wrote a piece in the New York Times that's really interesting. I'm going to read a particular piece that I'm interested in. We need telescopes of the mind to anticipate dark corners, well, that was coined by Bouchaud. Tipping points, this is another way to say that, or black swans. And here the point is really that whereas in physics we're extremely used to simulations, the fact that simulating artificial economies, for example, or simulating simple models that you cannot solve analytically, but you get some insight from these simulations, is something that economists are not well trained to do and are not accustomed to do. And in some, I have economist students as interns, and when they arrive, they've never been confronted with numerical simulation. They don't know what it is. So it's very striking. There's again a cultural barrier. And so what Buchanan wrote, Buchanan is a physicist who wrote many books of science, general audience science. And his piece was called "This Economy Does Not Compute," and he says, done properly, computer simulation represents a kind of telescope for the mind, multiplying human powers of analysis and insight, just as a telescope does our powers of vision. And I think this is really beautiful, a beautiful way to say that. With simulations, we can discover a relationship that the unaided human mind, or even the human mind aided with the best mathematical analysis, would never grasp. So, for me, the importance of trying to train physicists and economists along lines like this is an interesting and important program that will take decades, probably. You know that going from the project of having a numerical simulation to predict the weather was launched in the late 40s, but it's not until the early 80s that computers became better at predicting weather than traditional methods based on analogies, where people would flip charts of previous weathers, last century weathers, and would just compare the present situation with what happened in the past and say, well, this date corresponds to what happened 17th of September to 1902, say. That was the method, and this method, although human-based and pretty basic, was better than numerical simulation until the 80s. So it's not that agent-based models, that is, fictitious economies based on reasonable agents that do things, It's not that it's going to revolutionize the economy right away, but I'm really hopeful that progressively this will be a tool that economists use as well. And in this endeavor, the methodology of statistical physics, that many details disappear at the aggregate level. And so we don't necessarily need to describe humans extremely accurately. We just need to find the right biases of human behavior, the right human traits that survive at the aggregate level to maybe be able to explain crisis and so on. So I'm done. Thank you for your attention.
Is there already an impact of machine learning algorithm, deep learning, for instance, on understanding the hidden properties of microscopic states near first-order phase transition, for example? Because it's something that escapes to us. We see the transition, it's hard to predict, but something must happen at the microscopic level that signals that the probability to go.
So I've seen a paper recently about this. I haven't had time to read it carefully, but they are. I'm not sure it was machine learning, but they are in particular. It depends also on whether you're in finite dimension or if you're in a kind of infinitely connected system. The mean field times graph where there's no space, or whether you're in finite dimension. I think it's not at all the same. For example, in these mean field models, there's no precursor. I mean, when you know the model, it's always the same. Also, do you know the model? Do you know the underlying model, or don't you know the underlying model? And that's an argument that economists always make, and it's very difficult to get around it. They say, oh, but if you know the underlying model, then you're able to do things that you're not able to do without knowing the underlying model. And so if you're infinitely rational and you've been able to observe the economy for a long time, then you know which I think is just a figment of imagination. But it's very hard from a philosophical point of view to argue against this. But I'll try to find this paper again. It was in the archive maybe a few months ago.
So in physics we're quite used to distinguish, say, between equilibrium situations and non-equilibrium situations. But I expect when you construct stochastic collective models starting from, say, social forces, the situation may be even worse, that
yes.
Your forces are not, so don't obey Newton's law. You can't write anything like Newtonian and whatever.
Absolutely.
What is your experience? So how to map maybe some models to physics, or even if it's in many cases not possible?
No, you have a very good point. So this model, for example, so there's something called choice theory in social sciences, where people are supposed to flip from choice A to choice B according to some rule, and this rule is exactly a metropolis algorithm that obeys detailed balance. So why they choose this? Because they're able to solve the model. I mean, it becomes what they call a potential game. So there's Boltzmann-Gibbs measure at equilibrium and so on. And it's not really based on any, it's plausible, of course, I mean, that you choose a better choice with higher probability than the worst choice, and that there's a parameter that is a kind of temperature that encodes some irrationality. But there's no, as you say, there's no microscopic basis for that. They only choose it because it's solvable. And so, for example, something that would be very interesting to do would be to try to see whether these equilibrium statements that lead to a phase aggregation in this model still hold true when you violate detailed balance. But I think this is a completely open field, and it is an open field because it's very difficult, as we know. I mean, there's no general result as soon as you...
Schelling is a physicist?
No, Schelling is an economist. And Schelling wrote a beautiful book called From Micro Motives to Macro Behavior. So he's really completely in tune with statistical mechanics. But he was you know, for example, the way he arrived at this segregation result was based on not even a numerical simulation, an analogical simulation with coins that he would flip according to his rule and realize that it would segregate. But he didn't have any analytical insight into the model. Ooh, the forest of elves.
So I would like to understand more something about your comments on trying to train, for instance, economic students to the importance of numerical simulations. Obviously, this implies, as you say, the knowledge of models and also the limitations of models. Because when you make a numerical simulation, you must know what you are dealing with.
Yes.
This is very important. On the other hand, it seems to me that some of these models might suggest that you could, by taxes you the same in that case, force a system to go in some direction. And that's part of the story. Certainly it may help. It may be useful, but I have the feeling that a complex system should have in itself also different ways of, as you are saying, different levels of passing information between the agents in such a way that the system in some sense may divert to other directions, despite you try to drive it in another direction. So maybe there are some behaviors that are much closer to self-organized critical behaviors in these systems that may appear suddenly without any, as a collective effect, without any possibility even of predicting it on the basis of a given model.
Sure.
So in some sense, I was thinking about how would it be, for instance, interesting to use models where you have varying parameters in time that adapt themselves during evolution.
Sure, I mean, you can study, so for example, there are simple models of markets where there's a critical point in theory between, so this is the minority gain that people have promoted since the end of the 90s, where actually there's a phase where people cannot predict anything, so the market is quote-unquote efficient, so there's no way to make money out of the market, and an inefficient phase where you can learn the next move of the market, if you want. And if you add to this the rule where people try to learn where they are, and people who lose money just exit the market, and people who make money stay in the market, then you're going to force the system to go towards this critical point. Because if you're in the unpredictable phase, then people will, on average, due to costs, due to transaction costs, lose money, and so they will disappear. And if you're in the predictable phase, people will make money, and this will attract new players. And so, in the end, it converges to this critical point. So there are many models where you can do that. There are also models where you have this self-generated complexity, like ecological models, where species disappear, and you are always at the border of chaos.
At the end, you mentioned the analogy to weather forecasting. It took 40 years. The aim was clear. The aim was to get better forecasts, longer forecasts. What is the aim? Suppose this model or this program for economics will work. So at the end, we'll have a stable economy, or, I mean, is there some fixed point where this kind of endeavor should lead to?
No, you're absolutely right. Even because the problem is that this field is completely intertwined with politics, and even the models. If you look at the assumptions of the models, you can very clearly see that these models are not politically neutral. So for me, the first goal is to reach a kind of consensus on what's a reasonable description of how the economy functions. And then we can try to put other aims, like what do we want to optimize and things like that. Or is the system intrinsically unpredictable? Or what are the monetary rules that one should use to stabilize it? What are the feedback loops? I think what's striking is that people have no idea of the unstable feedback loops in the economy. it's really striking, and I'm struck every day by this. And again, the point is that, and that's what Bouchaud said explicitly. He said later in his paper he says the problem is that that we came to believe that this was how the world worked. This picture here. In this picture here, there's no unstable feedback loop. And so we're so far from having just a fast, reasonable description of the system we're talking about. Your question will come second.
We have David and Francesco Bernard.
Just a brief remark. The second model reminds me of a case where you can have models of absolute negative mobility. You push a particle to the right and it moves to the left. And this can happen even in equilibrium situation. You start with the equilibrium system, push it to the right and it moves to the left. And this is the kind of thing that happens there, right? And then you
I don't know models of that out of equilibrium. I don't know models of that in equilibrium.
Sorry?
I don't know models of the kind you just said in equilibrium, by the way.
You know?
No, I don't know models.
Oh, there are models.
They are in equilibrium?
Yeah, but the starting point is equilibrium. You push it, and then it moves the other way.
But isn't that against linear response?
No, because you can have... No.
It's a linear regime before.
No, it's even the linear regime.
Really?
Yes, this can happen. Because it's, when the driving force has, it's not a single parameter, can move in two directions, and, it's a matrix, basically. And the response, you have off-diagonal terms that can push it to backward. So this can happen. I can give you a
okay.
Yeah. So this reminds me of this kind of thing.
Well,
it's very non-predictable.
Yeah, okay. I'm not sure there's a profound formal analogy. Here, what happens is technically that even if each individual agent obeys detailed balance in his own utility, as I was saying, the global rule that describes the evolution of the system is also detailed balance, but the Hamiltonian, if you want, is not the sum of individual utilities. You have to construct, you can construct it, but you find that there is, you can construct it from individual utilities, but it's not the sum of individual utilities. And this is why the system evolves to the Boltzmann-Gibbs equilibrium of this other quantity that does not coincide. And in these cases, that actually does not coincide at all with the maximum of the sum of single utilities.
Okay, it's not a question, it's just a heretic comment. I see papers in what's called sociophysics, and I understand them.
Yes, you're right. Many papers are just appalling, but...
I always have this feeling that they observe some complex phenomenon, and then you do a simulation, and what you get out what you want to get out, and you tune the...
well, you're right.
You tune the thing that your simulation until you get what you want to get.
You're right. On the other
hand,
hand,
in physics, just one more sentence. In physics, there are some basic restrictions. I don't know. I mean, the conservation of momentum and energy. I mean, you cannot write a model which violates these things. I mean, if you do detailed balance, then that is based on some understanding that systems tend to go to equilibrium or something like that. And here in the sociophysics, I mean, there are no rules. I mean, there is an infinite space of parameters, and you pick one or two or three, and you get something out. And if it doesn't produce what you want, then you change, so what goes in comes out. And I have always this feeling that you don't learn anything. I mean, you started out.
Ethan, you're right, but there's always good science and bad science. And what you say is really a problem, actually, because it makes the conversation with economists even more difficult. Because it's much too easy for them to say, well, look at this paper. It's just crap, so why do you want me to believe that you physicists are eating?
I just wanted to hear your opinion about this.
So yes, it's embarrassing, And that's the way it is. On the other hand, you know, this is, I think, an extreme counterexample to what you say. This is a beautiful model that starts from...
Yeah, I wrote it down and sent me myself an email to look it up, but...
I'm sorry?
No, I just sent myself an email to look this up.
Okay.
But
there are some models like this that are really nice, that you know, start from something that has been observed, that try to explain it, and that, you know, the rules you can debate, but they are not worse than the rules used by economists and sociologists themselves. They're actually exactly these rules. And you're able to map out a phenomenon that's highly counterintuitive. So now, you know, maybe it doesn't describe anything. I mean, this model is not meant to be taken à la lettre. But it is very inspiring. You know, I think that the idea that the invisible hand can badly fail, this is absolutely non-trivial, because this is so anchored in the economist's way of thinking. And of course, you can see all the political consequences of believing that this is true. That, you know, to be able to say, well, in this simple example, you know, this doesn't work, and I can show it. And it's a well-known phenomenon in physics. Phase segregation, this we know happens, and this is what happened in such a world. So what about your... You know, I think we also need simple models to think.
Francesco.
No, but the discussion already touched, the comment that some economists I spoke with pointed out that there are strong feedback loops between prediction and then the market or the economy reacts to prediction in a way that weather doesn't, of course.
Yeah,
so, and they basically claim that this makes almost impossible to
yeah, I know, of course, this argument, but that's again because they're completely stuck in their rut, in the sense that they so strongly believe in, you know, efficiency and rational agents and so on, so they have this feedback loop immediately, but it's not what happens. I mean, I know examples of effects that have been observed and documented in the literature for years, and they're still present in financial markets, because what is always underestimated is the fact that most people don't care about science. They don't care about knowledge. They just do what they do. And there's a lot of human biases that are surviving, and, you know, the world is like this. So, of course, if everybody was rational and took notice of a paper that proves that some statistical effect is present, then presumably the statistical effect would disappear because of feedback loop. But it is not what happens. People just do their stuff. And we have to model the world as it is, not as it should be for the mathematical models to work.
What about the introduction of non-linearity in the analytical model? That coincides with the beginning of the invention of the field by physicists, and what about, the controversy between financial mathematicians and physicists?
Well, I think nonlinearity is too broad a term, you know, in the sense that, for example, chaos theory. This was looked at briefly by economists in the 80s, and they decided it was either, you know, it's also true that they have a tendency to stick to what they know, but it didn't have much of an impact. And I think the idea is that we really need to do things that they perceive as useful. So in the financial field, it's been easier because there's a lot of data, and the outcome of better models is more immediate. I think, coming back to your question, the questions are better posed in a sense, you know, because markets move all the time. There's data every day, even every hour, even every second. So if you have a better model, it's more easily noticeable, and you can say. And this is what happened actually in the financial engineering. You know, there's less and less pure mathematically trained people with a Gaussian obsession and so on, and more people with a pragmatic view on data and the fact that models should follow from data and not the other way around. But in economics, it's more difficult because timescales are longer, and so it's going to take a longer time for these ideas to penetrate.
The very last question.
Do you think that econophysics in some sense is just a branch of sociophysics because you want to study collective process of human beings, or is there something intrinsically different in physics?
Well, first of all, I've never really liked this name, but it's there to stay. I don't know exactly the definition of econophysics and the difference with sociophysics. I think there's a large overlap.
So for you, it's more
the problem is I'm not sure the name is very useful.
So you don't think it's econophysics?
I mean, the examples I gave here are more related to what you would call sociophysics, but there's a lot of work also related to financial markets that I don't think have anything to do with sociophysics directly. So where do you put these? I don't know. I'm a little suspicious about creating strict boundaries. So, you know, this is what it is. I don't know how to follow it. Is it interesting or not? I mean, coming back to Ethan's comment, is it good science or bad science? I think it's better.
Last comment, and then...
A brief comment coming back to Bernardo's question. So, synchronization is an example where non-linearity plays a role. So.
Oh, but in these systems, then there are non-linearities everywhere.
Okay.
In all these examples, here there's non-linearity. Yeah. So I'm not saying that they are not. I'm just saying that it's too broad a statement. You know, non-linearities can lead to so many different things, from dynamical systems to these things.
All the feedback can be described. Otherwise,
Okay, thank you very much. We start at 10 past 11. 10 past 11.